Alright, yes, it's over. Alrighty, good morning everybody. Welcome back to Galois Theory. Hope you all are enjoying your Thursdays. Hi, Lydia to you too, of course.
Hello, Lydia.
Plan for today is we're going to finish off our discussion of Euclidean domains by talking about GCDs. What are they in a more abstract sense? How do we find them? And then we will jump into our next major topic, which is going to be looking at UFDs, or unique factorization domains. I've got my usual office hours over the next few days. This afternoon from 1 to 2, tomorrow morning 11 to 11:45, Monday 11 to noon, and 1 to 2. Yep, you all have a new homework set posted, homework 2. If you haven't seen it yet, you should check it out. It's about first problem's about kind of general ring review stuff still, and the second one's about proving that the Gaussian integers form a Euclidean domain, which I think is a fun one. Homework 1, it's due today. Hey, how about that? It's your first homework. So make sure I have it before, I would say it's supposed to be due at the end of class, but just make sure I have it before the end of today. I'll be okay with that. If I don't have it before the end of today, I will be sad, and then when I grade it, I will be mad, and then when you get it back, you will be sad. So that's the way it goes.
Because the rip will be bad.
Because the vibes will be bad, and your grade will be had. I don't know where I'm going with this. Lydia, this means you too.
If you turn it in on time, that would be rad.
That would make me quite glad, yes. Alrighty, considering there's much fewer of you than there were, those of you who had me for abstract algebra knew it. No, it took forever to get things back because there were like 40 of these I had to grade. Now there's about less than a third of that, and so hopefully I'll have this back to you on Tuesday. Smack him, Matthew. Any questions or comments before we get started for today?
I get to do it.
I'm thinking about it.
Alright. How can you sum up the political views of a mathematician who lives on a farm? Best way to sum up the political views of a mathematician who lives on a farm is that they are protractor. Alrighty. Does anybody need a copy of the Euclidean domain packet? You do.
Yeah, first.
Oh, I did. Here you go. I'm just going to leave one here, and you can get one if you decide you need it. So last time, we introduced the idea of a special type of ring called a Euclidean domain, which is an integral domain. Again, integral domain means no zero divisors, meaning you can't multiply non-zero things together to get 0. Along with this norm, we call it delta, this function that goes from the domain to the non-negative integers. By the way, I polled all the math professors yesterday. More of them agreed with me that 0 isn't a natural number than that agreed with you all that 0 is a natural number. So yeah.
I'm not disagreeing with you.
If you said,
I'm mainly talking to Isaac here, but
Maybe we need some adjustments to that.
we need some adjustments in our students. That's a lot easier to do than adjustments in our faculty.
Wait, if you said more of them, does that mean some of them thought that 0 was?
Dr. Gabler did, yes.
Okay.
What does he know?
Okay, but he doesn't do that on the homework.
Say what?
When he has homework, Ed does not include 0.
Yeah, he can't even keep statements. Anywho, let's get back on topic. The idea behind this norm is it's a way of defining a Euclidean algorithm on a Euclidean domain, which is basically a way of saying, hey, given any A, B, any two elements in your domain, A and B, as long as B is non-zero, you can find a way to write A as being QB plus R. In essence, you can find a way to do long division with taking A and divide by B to get a quotient and a remainder of R. And the reason why we need this delta map is to make sure that our remainder is smaller than our B term, the thing we're dividing by. And since obviously greater than and smaller than don't necessarily have to mean anything in an arbitrary ring, we use this delta map to kind of give us a way to compare the size in some sense of the remainder of the B term, the thing you're divided by. So last time we looked at some examples of Euclidean domains, specifically the integers and real polynomials. We saw that the integers satisfy this if you let delta be just standard absolute value. Polynomials over the reals will satisfy this if you just let your delta map be taking the degree of your polynomial. And we proved some stuff about Euclidean domains last time, specifically that all fields are Euclidean domains. You could basically have any delta map you want as long as 0 maps to 0. And all Euclidean domains are also PIDs. They're principal ideal domains, meaning integral domains where every ideal can be generated by a single element. And what I want to do today with these Euclidean domains is I want to talk about the existence of GCDs and prove that you can define something, the greatest, I'm so used to saying a greatest common divisor of two elements in a ring, in a PID, and then after we do that, talk about how can we actually put this into practice in a Euclidean domain specifically. Any questions or comments before we get going with that? Groovy. So, how do we define a GCD when the idea of some element being greater than another element has no real meaning in a PID? Well, you can't really say, oh, it's take all the common divisors of A and B and pick the biggest one, because that has no real meaning. But you can define a GCD like this. Given some A and B, pick some common divisor of both of them. And again, D divides A just means you can multiply D by something to get A. So this just means A is equal to D times some D sub A, or some D sub A in your ring. So greatest common divisor is a common divisor of A and B that satisfies if you take any other common divisor of A and B. If D prime divides both A and B, then it also has to divide whatever you say is your greatest common divisor. So greatest in the sense of any other divisors have to be divided. Any other divisors of A and B have to also divide the GCD. So a slight tweak on what you would normally think of as greatest with GCDs. And it turns out that as long as you're working over a PID, you can guarantee such a D has to exist. But not necessarily that it's unique. So let's prove this. Alright, so yeah, we're on page like, what, 1, 2, 3, 4, 5, 6 or something in the packet. So we're going to let R be a PID. With A and B being non-zero elements of R. And we need to somehow show that there exists some element D that's going to satisfy all of these properties. So, how do we construct it? It's kind of tough, because we don't really know anything about our ring other than the fact that it's a PID. Meaning, any ideal can be generated by a single element. Well, a couple ways to go about thinking about it. The easiest way, I think, though, is to just take the ideal generated by A and B, where, as a reminder, if you take the ideal generated by multiple elements in a ring, like A and B, you're just looking at the set of all linear combinations of A and B. So, in other words, a set of all elements of the form AR plus BS. Where did that bullshit's coming from? I mean, where R and S are allowed to be any elements you want coming from the ring. Think again. Do I want to tell you that story?
Oh,
I'm not going to tell you that story.
you could do an office hours.
I want to get it started.
When are we meeting off for us?
You could throw it in.
Yeah, when are we all meeting?
It's a story of a foreign professor. When I took my second semester abstract algebra in undergrad, I had a professor say, something that could come across as extremely inappropriate because they didn't realize it was inappropriate. I'm going to leave it at that. So, we're going to consider the ideal generated by both A and B. So the set of all linear combinations of A and B in your ring. Lincoln, you look like you had an idea of what we might do with that ideal.
Oh, I don't know that I did actually have an idea. I thought I had an idea, but I don't actually think I have an idea.
You don't have an idea, just an ideal. Isaac?
Well, that should be equivalent or equal to a single, an ideal generated by a single element.
Yeah, we're working over a PID, so we should be, since this is an ideal, we should be able to find a single element that'll generate that ideal.
Maybe that.
Since there is a PID, we know we can find some single element that'll generate the ideal. And I'm going to call that element extremely suggestively
Oh yeah.
for some D in your ring. And then it's going to turn out, the rest of this proof is just showing that that D actually does satisfy the 2 bullet points that we needed to. That it's a divisor of A and a divisor of B, therefore, and any other common divisor of A and B will divide D. But yeah, that's how we find our D, is we just take the ideal generated by A and B. We know we're working over a ring where every ideal can be generated by a single element. Just pick a generator for that ideal. That's going to turn out to work, have the properties you want for a GCD. So, how do we actually prove that? First bullet point's pretty quick. We can say, then if the ideal, since A and B individually are elements of the ideal generated by A and B, you can always just write A as A times 1 plus B times 0, for instance, and similar for B. Since that ideal is generated by D, we know A and B have to be in the ideal generated by D. So in other words, A is going to be equal to D times some other element. What did I call them? A prime. And B is equal to D times B prime. For some elements, A prime and B prime, coming from your ring. That's just what it means to be in the ideal generated by D. The ideal generated by D is by definition the set of all elements of the form D times R, where R is allowed to be any element in the ring. So if A and B are elements of that ideal, then A is going to be D times something from the ring, and B is going to be some D times something from the ring. Which is the same as saying D divides A and D divides B. So we've got our first bullet point satisfied. Any questions or comments thus far? Second bullet point turns out not much more difficult to prove, just takes a little bit of work. We need to show that if D prime is any other element in our ring that divides A and B, then it also has to divide D. So we're going to suppose D prime is some element in our ring where D prime divides A and D prime divides B. Joe?
I forgot. Is there some reason that this is commutative or
Why this is commutative? Integral domains. Part of the definition of integral domain is that multiplication is commutative. Yes. Should have mentioned that earlier. It's not just no zero divisors. There's also the conditions that you have to have a multiplicative identity, so some element 1, and multiplication has to be commutative. Yeah, because if you didn't have commutativity, this proof still works. It just gets more annoying because then you have to worry about like we haven't talked about this, but there's something called left ideals and right ideals in non-commutative rings, where it's, instead of all things, it's like d times some element from the ring, which is not necessarily the same as a set of things from the ring times d. But for what we're going to be doing this semester, we're almost always going to be working over commutative rings.
Oh, we talked about it last semester with groups.
With what?
I don't think we did it this.
My brain was, we totally did it with groups.
Something you'd like to share with the rest of the class?
I think we talked about left.
We didn't do, I don't think we did left and right.
We did.
Ideals.
We did not.
Left and right ideals.
We did left and right.
We did-
cosets,
oh.
ideals.
We did cosets because we talked a lot about
We talked more
non-commutative
about
groups.
normal stuff. We talked about normal stuff.
In my section of 410, I can guarantee you we did not talk about left and right ideals.
We talked about normal.
Unless I mentioned it in passing.
Maybe I talked to you about it in office hours or something.
It's possible. Alright, so we're going to suppose d prime divides a and d prime divides b, and our goal is going to be to show that d prime also has to divide d. So what we're going to do is we use the fact over here that a and b are elements in the ideal generated by d.
Are we saying that d prime is not equal to d?
It could equal d.
Okay.
I mean, would you agree that d divides itself?
But,
So,
okay.
so yeah, I don't think we need to make any claims about d prime. If you really wanted to, you could break it up into two cases that way, but there's no need to. So here we use that a and b are elements in the ideal generated by d to write a and b in a particular way. Now we're going to kind of do the opposite. We're going to use the fact that d is contained in the ideal generated by a and b to write d using this sort of expression. So since d is an element in the ideal generated by, well, itself, which is equal to the ideal generated by a and b, there exists, what do I call them in my notes, r hat and s hat coming from our ring, such that d is going to be equal to ar hat plus bs hat. Put your mind out of the gutter going on. Well, we know d prime divides this term, d prime divides that term. Therefore, d prime is going to divide this term and that term. And if d prime divides each of these two terms separately, it's going to have to divide the sum, and that'll essentially tell us d prime divides d. So writing that out in words, we can say, since d prime divides a is going to be equal to d times, what do I call it? A is equal to d prime times d sub a. And since d prime divides b, b is going to be equal to d prime times d sub b for some d sub a, d sub b coming from your ring. Well, then we can write out d as being equal to ar hat plus bs hat, which in turn is going to be equal to d prime times d sub a r hat plus d prime times d sub b s hat, which in turn is going to be equal, doing a little bit of associativity, to d prime times the quantity d sub a r hat plus d sub b s hat. You okay?
Yes.
You sure?
I didn't notice you have a desk in front of you.
5.
He does have a desk in front
I
of him.
didn't notice that before.
And it's d prime divides d. And there's our proof. We just showed that d is a multiple of d prime, which is the same as saying d prime has to be a divisor of d in this circumstance.
So if we have multiple numbers, each of which divide the other, can all be?
So say again, if D,
I mean, if there are more than one number, like if there are two numbers that both divide each other
in the ring,
right? Then can they both be?
sure. You could have the GCD. Sure. So like, if you were to ask me in the integers, for instance, what's the GCD of 4 and negative 4? I would say 4. Or negative 4. So before we go on to start talking about uniqueness, any questions about this proof of existence of a GCD? Once you know that the GCD of 2 elements in your ring exists, you can also show, it's not too hard to generalize that to showing you can take the GCD of 3 elements, or 4 elements, or k elements for any finite number k in your ring. And that gets spicy when you actually try and compute GCDs using that method. But before we start talking about how to compute GCDs, I want to talk a little bit about uniqueness. Because in general, you're so used to growing up to thinking about the GCD, but there's nothing in this proof that guarantees D has to be unique. In fact, any element that will generate the same ideal as D would fit the same job, would do the same job. Because this is the only how we define D, is just pick some generator of the ideal that is also generated by A and B. Any element in this ideal that generates it would also get the job done just as easily. So make a note of that over here. Is everyone okay if I erase this first half? Let's say D. All right, here's a question for all of you. How could we form, what element is necessarily going to generate the same ideal as D? Lincoln?
I was going to say D inverse if it has one, but
D inverse if it has one. Although if D has an inverse, then this ideal would just be the whole ring.
yeah.
So that would that would basically be saying A and B are relatively prime.
What about D squared?
What about D squared? Turns out you can say a nice relationship between these two ideals. Not a subset, other way around actually. Because anything that's a multiple of D squared is necessarily going to be a multiple of D. And not necessarily vice versa. It's like saying, for instance, the even integers contain the integers that are multiples of 4, but not the other way around. You can have multiples of 2 that are not multiples of 4, but all multiples of 4 are necessarily going to be multiples of 2. Turns out, just multiply D by any unit in your ring. In other words, multiply D by any element in your ring that has a multiplicative inverse, and that's going to generate the exact same ideal. Not even D, but for any unit. Coming from your R. Or again, unit just means element with multiplicative inverse. And hence, and by the same, and what this tells us is that if D is a GCD of A and B, you can multiply D by any unit, and you'll get another GCD. Well, the same one if your unit happens to be 1 specifically. So as a quick example of that, if we were to just look in, I don't know, integers. That's a nice PID. What are our units in the integers?
Well, we have one.
That's it.
No, that's not it.
In the integers, there's only two elements that have multiplicative inverses, 1 and -1, which are each their own inverse. There's no other integer you can multiply by some integer to get 1. And so, for instance, if we wanted to take the GCD of 4 and 6, what would your high school algebra Matthew tell you is the GCD of 4 and 6?
I'd say 2.
2 works well as a GCD. Since, why? Because if you were to take the ideal generated by 4 and 6 in the integers, that's going to give you the same thing as the ideal generated by 2, which is just the even integers. Because any even integer can be written as a linear combination of 4 and 6. Isabel, what else would be a GCD of 4 and 6 in the integers other than 2?
4.
Not 4. 4 doesn't divide 6. Well, we said that if you multiply the GCD by any unit, you'll get another GCD. And if our units are plus or minus 1, what can you multiply 2 by in order to get a different one?
Sorry, I'm confused on what you're asking.
Sure, no worries. So basically I'm saying, if this is our D here, what elements can we get from multiplying D by our units? What's 2 times 1?
2,
What's 2 times -1?
-2.
-2 would also be a GCD, according to our definition in the integers. Because plus or minus 2, they're going to generate the exact same ideal, which is the even integers. So, moral of the story is GCDs are not unique.
Especially not the real numbers.
Especially not in the real numbers when suddenly,
Everything
Let's-
is a unit.
well, yes. Yeah, in a field everything is a unit, so the concept of GCD has no real meaning. If you want a slightly more interesting example, you could do, say, real polynomials. And if I wanted to ask you, say, for instance, what's the GCD of,
What's on the packet?
I know, say x cubed and x cubed plus x. Matthew?
Just X.
Well, let's see, this is x times x times x. This is x times x squared plus 1. I would certainly agree that x is a common divisor of these things. If you take any other common divisors, does it have to divide x? I'd say so, because any other divisors are just going to be non-zero constants or non-zero constants times x. In order to be common divisors of this, yeah, I would say x.
Or 3x.
Or 3x.
Pi x.
Or pi x. Or square, or x over 2. Or square, or x times square root of pi over 17. Or c times x for any c not equal to 0. Constant c. The idea being the units in this ring are going to be any non-zero constant. Because in the reals, any non-zero constant you can multiply by another non-zero constant to get to 1. Whereas anything with degree 1 or more, there's no polynomial you can multiply it by to get to 1. And so if x is a GCD, that means you can multiply x by any unit and find another GCD. So any non-zero constant times x would serve as a GCD. Matthew, did I answer your question?
Yeah.
Cool. Here you only have 2 units, so in the integers, you're only ever going to have 2 GCDs. And a ring like this, where you have infinitely many constants, you can have infinitely many GCDs. Yes, Eleanor?
Are there rings that have only 4 units?
Sure. Zmod, well,
Yeah.
I don't know, you had an example last time. I gave y'all had an example in like last semester, right? Asked you like that on the homework, I'm pretty sure.
Wouldn't
Yeah.
Z1 5Z
Oh, yeah.
Zmod 5z? Zmod 5z is a better one, and that one's actually an integral domain, so,
Or Gaussian integers.
or the Gaussian
That's
integers,
the
if
one
you
I
want
was
to get more clever about it. Trying to avoid bringing that up, because I don't want to spoil too much on your next homework. Yes, there are rings that can do that. For any n, you can find a ring with n units.
How's a complex space in 3 dimensions?
Any other questions?
What about the quaternions?
Any other? What's your ring structure on the
It's
quaternions?
probably a lot.
I don't know, man.
No.
I imagine you make it up.
If it's 1, does
But
it
that
have to
would
be
not
that
be.
is 1? Would it have to be the triple?
If what?
If there's only 1 unit?
Well, if there's only 1 unit, that means -1 is equal to 1, and if -1 is equal to 1, then 0 is equal to 2, and if 0 is equal to 2, then
You're working
over a ring of... Not necessarily, you're working over a field of characteristic 2,
Yeah.
which as we've seen, could still be an infinite ring. You could have something like that would be an example of a PID with only 1 unit.
Oh yeah.
It's one we might be seeing more of later in the semester.
No, it's not binary, it's
What?
unary.
No, it's binary. You have 0 and 1.
Yeah.
Zmod 2 has 2 elements. It's just that
Z1
0 doesn't count as 0 isn't a unit though, so it only has a single unit. But
But if you did
It's 2 constant terms.
If you did Zmod 1, that would be.
Zmod 1 would be trivial, and that would technically have 1 unit because 0 is equal to 1, and so 0 times 0 equals 0, therefore 0 has a multiplicative inverse of itself.
Yeah. See, I read that as
Zero is a
Z
great
rather than
divisor.
Z2, so.
That is technically true
Oh.
in that ring.
Yep.
In that ring.
So how do we actually compute GCDs in these crazy rings? Turns out in an arbitrary PID, finding greatest common divisors is annoying and hard, and I don't really want to talk about it too much right now. But if we're working over a Euclidean domain, which we know we proved last time, all Euclidean domains are PIDs. So all Euclidean domains should have GCDs. Turns out we can use the Euclidean algorithm to help us out quite a bit. Let's take a look-see. So if you've had number theories, some of what we're about to do is probably going to look familiar.
What if you have
Then prepare to be amazed. So, as an example, let's just do an example over the integers, and let's take the GCD of 372 and 102. Yeah.
2.
The answer is not 2.
Oh,
Six.
darn.
It is 2 is a common divisor. I will give you that.
It's
Yeah.
-6.
Oh.
-6 is an answer, yes. The answer I'm planning on arriving at is 6, but -6 also works, yes. So how do we get there? Other than just kind of a brute force plug it, guess and checks sort of
with
approach.
Dr. Driscoll specifically?
With me at your side, any problem is solvable. Well,
That's so inspiring.
Essentially, you subtract one term from the other until the other is small. Okay.
Small.
First we're going to subtract 102 from 372 3 times.
And okay, why 3 times?
Because it will get 307 because 372 minus 306 is smaller than 102.
So what Lincoln is essentially saying is he's using the Euclidean algorithm.
Right.
This is the complicated way to solve the
So here's what we're gonna do. This is gonna be our A. This is gonna be our B. We're gonna do the Euclidean algorithm, find our Q and R that will do the job.
The actual.
Specifically, we don't really care about the Q. We want to find the R when we take A divided by B. So let's Euclidean algorithm it up. So blank times 102 plus blank. Lincoln says he thinks 102 goes evenly into 372 3 times. So that's our Q. And what does that leave us with as a remainder? 66. Yeah, there we go. That's our remainder. The first time.
And now it's time to divide 102 by 66.
Exactly.
Whoa, we're doing
I don't
the long slope.
Because
So what?
I'm giving you an
Ignore what I
approach.
just said.
I'm giving you an approach that not necessarily is the most computationally efficient for the integers, but is something that can be generalized to an arbitrary Euclidean domain here.
Oh, that's why we're doing it this way.
Oh, it's like long division.
Oh, it is like long division.
Oh my goodness.
So here's what we're gonna do. We're gonna replace A with our B term, 102. We're gonna replace our B term with our original remainder term. And now what we're gonna do is we're gonna find a new Q2 term and a new remainder term.
Oh, that's so fancy.
Okay, I don't know why we're all talking like this, but sure. I'm on board. So let's see. Isabel, redeem yourself. How many times does 66 go evenly into 102?
Once.
What's our remainder?
36.
I like it. 36. You have something you need to say, Eleanor?
I just don't know why we're doing this.
After we do this a couple times, we'll go through the theory behind why this approach works.
Okay, cool.
Now what we're going to do,
No, we don't see number theory.
this number
Thing.
goes here, this number goes here, same thing's going to happen again. This number is going to go here, and we're going to take our R1, oops, no, goes up there, and our R2, and do the Euclidean algorithm on that.
It's just long division.
It is just long division.
Yes, that is correct. This is long division.
How about that? So, hey Eleanor, how many times does 36 go into 66?
That's just one time.
Hey, that's not too bad. How about, what's our remainder?
30.
Hey, how about that?
I definitely wasn't gonna put any other numbers. I just can't count. It's fine.
Let's keep going. R2, we're going to divide by R3 and get a new quotient, Q4 and R4. So this goes there, this goes here. R2 is 36, R3 is 30. Jackson, how many times does 30 go into 36?
One time, remainder 6.
One time with the remainder of 6. Holy moly.
You know, I thought R2 was D2.
Best Star Wars character, bar none. And now let's do it again. R3. R4, see what you can do with it. It's going to be 30. Is equal to something, what are we at now? Q5 times our R4 of 6 plus our fifth remainder. Pete, how many times does 6 go into 30?
5 times.
5 times, with the remainder of?
0.
Holy smokes, our remainder is 0. And we can't keep going from here unless we want to be dividing by 0. Don't do that.
do that.
Alright, you do that. You do that. Tell me how it works out. Actually, no, we can't, because our definition of Euclidean domain literally forbids us from having b equals 0 and doing this. Otherwise, we can't make the delta condition satisfied. So, how do we find our DCD? Just go to the last non-zero remainder term. Boop, there it is. Or there, excuse me, Jonah, there is one of them. And then the set of all GCDs would be, and then if you want to find all GCDs, just take 6 and multiply by any unit, say plus or minus 1. So that tells us we're going to get plus or minus 6 as our GCD. You just do the Euclidean algorithm over and over. Each time you're taking the old b and the old remainder and making them the new a and the new b, respectively. And then if you keep doing that until you get a remainder of 0, and then the last non-zero remainder is your GCD. Any questions or comments relating to that? Let's do another one, but with polynomials this time. What do I have? X squared plus 7x plus 6, x squared minus 5x minus 6. Work 1 is still due today, even if I erase the announcement.
Oh, is it?
So let's find, so this time, let's go over to another Euclidean domain we know and love, the real polynomials. And we're going to compute GCD of x squared plus 7x plus 6 and x squared minus 5x minus 6. Oh boy. Well, first of all, these are the same degree, so I think we could choose either one to be our A and our B. Usually you want your A term to be the one with the bigger norm value. In this case, the bigger number. In this case, you would want the A term to be the one polynomial with the higher degree, which in this case, they have the same degree. So, x squared plus 7x plus 6 is going to be our A. It's going to be equal to something times our B term plus something. QB is x squared minus 5x minus 6. All right, Emily Rose, what's our Q, what's our R?
Q is 1 and R is 12x plus 12.
Like that?
Yeah.
If you add, okay, multiply by 1 doesn't do anything. If you add these, you'll get x squared plus 7x plus 6, which is what we wanted. Does your R satisfy the delta condition that we need, where delta of R is less than delta of B, meaning R is a polynomial of smaller degree than B? I'd say so. This is smaller degree than that. It's degree 1 versus degree 2. So the delta condition is satisfied, and I think the Euclidean algorithm checks out on that one. So let's repeat the process. Let's get some R2s up in here. So now we'll take B, our x squared minus 5x minus 6 term is going to be equal to some Q2 times our original remainder term, 12x plus 12, plus some new remainder term of smaller degree.
What if we made it x over 12?
Where?
An equation.
Okay, what would this be then?
That would be. I saw it pretty back hard.
So that would give us, so if we multiply that out, that would give us x squared plus 1.
Negative 6x.
Wait, x
No,
x squared plus x.
No,
It would be x squared plus x.
Wait,
X squared plus x
What?
here.
No,
No,
It-
no,
it
in
would be
R1.
x plus 1.
In R1. Why?
No.
No.
It's,
Yeah, that's-
so it's not x squared plus 1,
1/12
it's x
times
squared
x
plus
minus
x.
6.
Yeah.
Subtract.
Oh, because 12x over 12 is x, not 1. Durr. Okay, so that would, okay, so if we did x over 12 here,
Yeah,
that would give us that, and then we could add,
6x minus.
What?
or-
so like a negative
or-
6x minus 6.
Yeah.
Isn't, oh, wait. Is it plus?
No,
It's negative, yeah.
no.
Why no?
Because the degrees are the same. It doesn't work. Delta does not.
Oh my gosh, we need this to have a smaller degree than that.
X,
So while that does satisfy the A equals QB plus R equation,
x over 12 minus 1.
It no work.
Yes.
it doesn't give us the delta condition that we need.
Oh, I don't like that.
No, I didn't like your answer, so there. Anybody have a different one? John?
X over 12 minus 1 half.
Like that?
Yeah.
So if we multiply that out, we'll get, oh gosh, x squared minus 6x plus x, so minus 5x minus 6. Oh, hey. Ain't that something? You got a remainder term of 0. So it's our GCD. Matthew?
It's cx plus c.
Oh, very clever. I was hoping you'd say 12x plus 12, and I'd say, yes, it is that, times any unit, which would be any constant. Yeah, so technically it's going to be any constant times 12x plus 12, which is equivalent to saying just anything of the form cx plus c, c not equal to 0. And in fact, if we take a look at the polynomials we started with, I was curious if anyone was going to suggest this to begin with. If we factor this, what are we going to get?
I did that.
Oh, aren't you special? X plus 1 times x plus 6. And this one,
X plus 1 times x minus 6.
x plus 1 times x minus 6. So what's the greatest common factor here? X plus 1.
Well,
Or any constant multiple thereof, which is equivalent, Matthew, to what you said. Because the non-zero constant multiples of 12x plus 12 are exactly the same as the non-zero constant multiples of x plus 1. Because, I mean, you could always do something here like herp and derp. I'm going to multiply this one by 12 and divide this one by 12. Get something like that. And do the same here. 12x plus 12 times x over 12 minus a f. Have we seen this before? Oh, yeah. And say, hey, look, they have a common factor of 12x plus 12. You can multiply your final answer by any unit and still get a valid GCD. But the moral of the story is the same approach that works here, or the same approach that works here will also work here and really in any Euclidean domain. You just have to keep applying this process over and over until you get a remainder of 0. And once you do, just go back, circle back and take your last non-zero remainder to validate the GCD. Any questions or comments about this? Is that an answer? No. Okay then. So, why does this work? Turns out you can actually prove this algorithm, just the algorithm of repeatedly applying the Euclidean algorithm and then swapping old B becomes new A, old R becomes new B, until you get a remainder of 0, then take the last non-zero remainder. Turns out that'll work over any Euclidean domain. Seamus?
It comes from the fundamental
equation of if you have anything divisible by D, so if you have A is divisible by D and B plus C and B is divisible by D, then C must also be divisible by D, which means that since we're looking...
Divisibility works nicely with regards to linear combinations.
That's right, divisibility works nicely with regard to linear combinations, which means that since we're looking for the greatest common divisor of A and B here, and we have our remainder, we know that whatever we're looking for will divide both A and B, therefore it must also divide the remainder.
Essentially, yeah. Let me get a better piece of, not just a better piece of chocolate. I got a better piece of chocolate.
Yay!
That's gonna have to leave the room. And now, let's go ahead and demonstrate that. Let's work through an arbitrary example over an arbitrary Euclidean domain and show that that comes out.
And do we know that it'll stop because of the delta function will keep getting smaller?
Yeah, I was planning on asking you all that here in a minute. Like, how do we know this process will repeat in a finite number of steps? It's because delta, again, is restricted to only returning values of non-negative integers, and since delta has to be getting strictly smaller each time you apply the Euclidean algorithm, if your first remainder is a delta value of, say, n, you'll only ever need to apply the Euclidean algorithm n times at most before you get to 0, and necessarily, and the process will have to end. So let's take a look-see at this. So get ready for a little bit of a mess. So let's say we start off with some A and B. All right, let's do the Euclidean algorithm to get A equals Q1B plus R1, where delta of R1 is necessarily going to be strictly less than delta of B. At the back of the packet now, if you're following along there. And then we're going to keep doing this. We'll say B is equal to some Q2 R1 plus R2, where delta of R2 is necessarily going to be strictly smaller than delta of R1. In other words, the second time you apply the Euclidean algorithm, the second remainder has to have a smaller delta value than your first one. We'll take R1 to be some Q3 R2 plus some R3, where delta of R3 is smaller than delta of R2. And then we just keep repeating this process for as long as we need to. And eventually, we're going to get to the point where we have some, all right, it is R sub k minus 3 is equal to Q sub k minus 1 times R sub k minus 2 plus R sub k minus 1, where delta of R sub k minus 1 is necessarily less than delta of R sub k minus 2. And then in our final step, we'll eventually have to get to the point where we get R sub k minus 2 is Q sub k times R sub k minus 1 plus R sub k, where delta of R sub k is 0, meaning that R sub k itself is going to have to be 0. Dr. Gerstle, what on earth are you doing? Big mismatch to show what this process ends up looking like in an arbitrary Euclidean domain. And my claim is that's our GCD right there. Well, that's the GCD right there. Not delta of that, but just R sub k minus 1. So let's prove that. So we can analyze this. We're going to use the fact that all Euclidean domains here are PIDs to just look at the ideals that come along the way. And we can say that from the first line, we know that any element that's in the ideal generated by A and B is also going to be in the ideal generated by B and R1. So why is that? Well, because if we were to take some arbitrary element in the ideal generated by A and B, we can take that arbitrary element in the ideal generated by A and B, which is just some linear combination of A and B, and we can write it in the form AS plus BT is equal to Q1B plus R1S plus BT. In other words, we're just substituting in this first line of the Euclidean algorithm for A. Yes, there's like 50 variables floating around on the board. My response to you is get over it. What can we do with that? Well, you can multiply that out. You'll eventually get Q1S plus T times B plus BT, or plus, not plus BT still, SR1. And this just comes from doing a little bit of multiplying out and distributing. If you multiply this out, you'll get a Q1BS plus R1S. So this plus that, and then we'll have a BT left over that comes from here. This is from doing some redistributing.
It is really hard to tell your Q's apart from your A's.
Yeah, I was looking at
That's
that.
what I'm really having a problem
Oh,
with. not
sorry.
the number of them.
Here, I'll try to make it a little more clear.
The one on two.
I don't like that. Okay.
Wait, so is that also a Q? Oh, it is a Q, okay.
Okay. Yeah. Sorry. I'm so used to recognizing my own letters. But what do we know about this? This is in the ideal generated by B and R1. Because it's something times B plus something times R1. What's that? Zooey mama. So in other words, this is a subset of that, is what we just proved. We can also prove the other way around, that any element in the ideal generated by B and R1 is also going to be in the ideal generated by A and B. By saying any element in the form, what do I call it, xb plus yr1, any element in the ideal generated by B and R1 is going to satisfy xb plus yr1 is necessarily going to be able to be written in the form xb plus y times the quantity A minus Q1B. Why? Because if we take this equation and solve it for R, this is just going to give us, or solve for R1, we're going to get R1 is equal to A minus Q1B. So I'm just doing another substitution here for R1, which if we write this out, we can do a little bit of redistributing to get x minus y Q1 times B plus y times A. Because in both cases we have xb, ya, and yq minus yq1b. They come out to the same thing. But by rewriting it in this way, we get thing times b plus thing times a. That has to be in the ideal generated by a and b. This isn't a, by the way, not h. What's our ultimate conclusion here here's the main takeaway after doing this sort of annoying algebra with variables. Eleanor?
A and B is equivalent to B all one.
Yeah, the two ideals have to be equal. So this is going to tell us that the ideal generated by A and B is going to be equal to the ideal generated by B and R1. Because any element in either of these ideals has to also be contained in the other. They're both subsets of the other one and thus have to be equal.
Just repeat this over and over and over and over and over and over again 8 times.
Which, by the same logic, has to be the same as in the ideal generated by R1 and R2, which has to be the same as the ideal generated by R2 and R3, which has to be the same as the ideal generated by K minus 2 and RK minus 1, which is the same as the ideal generated by RK minus 1 and 0, which was our R sub k, according to what we did over there, which is equivalent to just the ideal generated by R sub k minus 1. Because taking linear combinations of R sub k minus 1 and 0 is just going to give you taking multiples of R sub k minus 1, hence, thus, the GCD of A and B is going to be R sub k minus 1.
As is obvious to the casual observer.
Oh yes. Times some unit. But this will be a GCD of A and B. It's just the last non-zero remainder you get when you take this Euclidean algorithm process to its conclusion. So this basically just kind of generalizes that result from number theory that says if you want to find GCD, you can just do repeated Euclidean algorithm and take the last non-zero remainder. Turns out an arbitrary Euclidean domain means the same. Because the ideals kind of all turn out to be the exact same as each other by repeating this logic over and over and over until eventually your remainder term goes to 0. Y'all doing okay? How are we doing? Oh no, classes ended 2 minutes ago. To look at Emily Rose, because she's reminded me the last 2 times. Nope, that's not the case. So, that's all I have to say about Euclidean domains for now. These are going to come into play quite a bit here in a few weeks once we start really diving into the Galois theory proper. But there's one last type of domain that we need to introduce to our cast of characters. The one that fills in the blank that I mentioned at the end of class last time in this hierarchy of things that come between fields and integral domains.
Unidentified flying domains.
Unidentified flying domains. Here's yours, Lydia. I'll keep it in my office till you pick it up. And that is unique factorization domains, which, as the name suggests, is an integral domain where every term can be factored into uniquely into a product of irreducibles. I say uniquely because existence of units throws a big wrench into what is considered unique here. So, something we have used probably in this class at least a few times if I stop to think about it, many times in the course of Math 410, a gazillion times if you took number theory, is the fact that you could take an integer and write it as a product of primes.
Yeah.
We're going to be talking now about integral domains where you can do that, where everything can be written as a product of primes. Oh wait, did I say primes? I meant a product of irreducibles. Which may or may not be the same thing as a prime. So, what are our building blocks here? So our irreducibles are just going to be non-zero units that can't be divided into two non-units. So we're going to assume we have some integral domain D. Some element A not equal to 0 in our domain is irreducible. If two things happen. First of all, A can't be a unit. Sorry, -1, you don't count. And second condition, if A is equal to B times C for some B, C elements in your domain, then either B or C has to be a unit. In other words, an irreducible term is one that can't be factored into two non-units. Again, unit being something that has a multiplicative inverse to it.
So this means there are no irreducibles in the real numbers.
That means there are no irreducibles in the real numbers, correct? Because every real number is either going to be a unit or 0.
Yes.
Correct. So that means when we're looking for irreducible elements in our ring, we're probably not going to be looking at fields very much. Really. So let's do a few examples. All right. I know many of you all know this. What are irreducible integers commonly associated with? Or misassociated with, as the case may be. Primes! Yeah. We can say n is irreducible if and only if n is prime. So, for instance, Matthew, favorite prime?
I like 11.
11. How many ways can we factor 11, or write 11 out as the product of two integers? I can think of at least a couple ways. Isaac?
-11 times 1.
-11 times 1 is not equal to 11.
Negative. You didn't hear the parentheses?
No. Gosh, I had this big discussion in both my 105 classes today. They were asking me because we're doing these sort of compound and implication statements where there's parentheses flying around. So Dr. Gerstle, when did the parentheses matter? That led to a big debate in both classes. They're sometimes they matter a lot, sometimes they don't matter at all, and you kind of just got to know from working with them on. How else? Andrew, can we factor 11?
11 times
11 times 1. Any other ways? Using integers only?
-1 times -11.
1 times 11.
Any other ways?
Well, actually, you can only do 2. Never mind. I was about to say, you could do 1 times 1 times 11, but that would be 3 factors.
I'm specifically looking for 2, yes. All right, here we go. What do you know? Unit, 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 unit.
That's going to be a coincidence.
If you want a non-unit way, we just I just need to have students in here that aren't slackers like you. Whereas, we can contrast that with something like, Jackson, what's your favorite composite number? Non-prime, don't give me plus or minus 1.
Yeah, 16.
Or 0. 16. Sounds great. 60 would also work.
60 has so many factors. That's why the
Yeah. Well, I'm not going to list all of them either for 16, but lots of ways of writing 16 as a product of two non-units.
701.
No. 16 over 720 is not an integer, sir. But you could write it as, I don't know, 2 times 8. Or -4 times -4. Or 4 times 4. And if you notice, none of these require using units. So this one is irreducible. This one is not irreducible.
As in it's reducible.
As in, it's reducible. Yes, actually.
Two. Lots of things.
I know, it's always weird defining something by defining what it's not first. So eventually our definition of reducible is going to be it's something that is not irreducible, which is saying, oh, reducible is defined to be not reducible. But that's the way we do it.
It's like everything about the null set. It's not
I actually defined vacuous truth today in my 105 class as well. And they had a fun time thinking about what that could mean. All right, so that's kind of the integers. Basically, irreducible if and only if prime. Let's do root balls. Or as previously mentioned, our units are going to be any constant not equal to 0. Am I using that tiny note? So, I don't know, how about 2x? Is that irreducible? Isaac?
No.
Okay, give me 2 non-units that multiply together to give me 2x.
1/2 x and 4x.
That does not multiply to 2x,
No,
sir.
it doesn't.
You have a better way in mind?
No, because now it's gonna be a problem.
If I gave you 2x squared, you could do that. Parker?
I'm just gonna go out on a limb and say it's not possible.
It's irreducible.
That was just for you.
Yeah, it turns out all linear polynomials in this ring, meaning degree 1, they're going to be irreducible. Well, all non-constant linear polynomials are irreducible. Degree 1 polynomials. Why? Because the only way to break up degree 1 polynomial into a product of 2 things is degree 1 times degree 0, and degree 0 polynomial is going to be a unit. On the other hand, let's say we have some let's say we have a degree 2 polynomial. Is that going to be irreducible?
I think that one
I
is.
think that one is.
Oh, hey! Aha, I was trying to trick Isaac into saying, okay, that one you could do that for.
Well, I've learned that I can't multiply today, so I kind of stopped answering that.
I still try.
Alright, Isaac. I'll give you this one, and this one is not a trick question. Is that irreducible?
Then you can do 5x and x.
Then 5x times x. Neither of these are units because they're both non-constants. So this one is not irreducible. But x squared plus 1, despite being a degree 2 polynomial, is going to be irreducible. There's no way to write x squared plus 1 as a product of 2 polynomials without at least one of those being a unit. Over the reals, at least, because I know that's what Jonah's thinking right now.
Yeah, I was about to say, so I assume that holds for just about anything that has complex roots. Instead of real roots.
Well,
Since it's-
okay, what can we say about complex polynomials?
Wow! On the other hand, those are
Because there the irreducibles are a little bit spicier.
Yeah, because that x squared plus 1 would factor to x plus I times x.
Yeah, x squared plus 1 is no longer irreducible.
But something like 2x still is, right?
Sure. What's our our units are going to be the same. Well, the same in the sense that it's all non-zero constants. We now have a lot more constants to work with. Take I. Like I, for instance, negative I. So what can we say about This x, by the way, is not the same as that x.
As a hypothesis, it might be that it has to be degree 5 or higher.
Degree 5 or higher? To be irreducible? Why degree 5?
Because
Here's where you're getting that from.
quintic.
But those are factorable in complex.
Oh.
Everything has.
You're thinking of so the degree 5 bit, and we're going to get to that in like
Yeah.
a couple months from now. That's equations that you can solve using nothing but like your basic arithmetic operations, plus, minus, times, divide, and square roots.
Okay.
That you can't do with degree 5 and higher. Turns out.
What?
Over the complex numbers.
That's kind of crazy.
Why? Because fundamental theorem of algebra says that any complex polynomial, any non-constant complex polynomial can be factored into linear terms. Dr. Gersta, what madness is this? Take complex analysis this summer in the first summer session if you want to see a proof of that. But we are out of time for today. So, yes, we are actually out of time for today. So, hope you all have a good one. We'll pick up this discussion on Tuesday. What are we going to prove on Tuesday? We're going to prove that UFD, well, first of all, we're going to define UFDs. And then we're going to prove where UFD lies in our hierarchy, which is that all PIDs are UFDs, but not vice versa. And then we'll go from there.
Anyone who wants to do math competition, I have pizza.
UFD, PID, OMG, go get pizza, have fun. Catch you video.